Assalamualaikum warahmatullahi taala wabarakatuh, and very good evening everyone. So let's start the class with the Ummul Kitab Al-Fatihah. Cool. So let me share the slide first. So the topic for today is the rotational motion. Okay, rotational motion. Right. So what is rotational motion? Okay, it's about a motion that meets a certain terms in this topic, okay, can be contra or can be referred to what we call in motions that we learn about kinematics, such as displacement, velocity, and also acceleration. Okay, but right now we are talking about motion in rotation. Okay, rotational motion, that means pergerakan di dalam bulatan. Okay, so these are the learning outcomes for the topics of rotational motions. Okay, for example, we can define the angular position and angular displacement, as I said to you. Okay, when we talk about position, so that means we know it's about location, location, and it can be referred to, and it can also relates to the displacement. Define average and instantaneous angular speed. Define an average and instantaneous angular acceleration. Solve problems involving angular variables. Identify the correspondence between the equations for linear motion at constant acceleration and those for angular motion. Okay, we also can apply the rotational kinematics equation for object undergoing constant angular acceleration. Lastly, to apply the relationship between the angular and linear quantities. Okay, so let's go to the topics, towards the topics, right? So when we studied about linear motion, okay, when we studied about linear motion, we needed to understand the concepts of displacement. Am I right? Okay, the delta x, for example, delta x means a change in position or change in the location, which means the final position minus initial position. So another part is a velocity v, okay, and also acceleration a. So each of these has its analog in the rotational motion. Okay, when you look into displacement or delta x, okay, or in your words it's s, okay, the delta x, okay, it can be referred to the angular displacement. Okay, when you talk about delta x, which is the displacement, that means in linear, okay, in the basic conditions, linear, so it can be relates, okay, it does not equals to, but it can be relates to the delta theta. What is delta theta? Delta theta means the angular displacement. Okay, and it can also, for example, we have v, a velocity in linear motion, so it can be referred to, or it can be relates to the angular velocity or omega here. Omega, a Greek words. Okay, and the acceleration, okay, in linear, okay, a is one, can be referred to as an alpha, which is the angular acceleration. Everything got angular, angular, angular. Okay, so that means in rotational motion, we must discuss and everything about the same goes to what we learn in linear motion. For example, we learn about displacement, we learn about velocity, we learn about acceleration. So in this case, in rotational motion, we learn about angular displacement, angular velocity, and angular acceleration. Okay, so you need to memorize, you need to look into a different perspective when you talk about uh, some terms that use in the linear motion. So here, okay, we use a little bit different compared to linear, which is it related to some angular, which means every terms in linear motion, we discuss it in terms of angular of it, which is when you look into the words angular, okay, the terms angular comes from the root word of angle. Angle means a darjah, or angle means a certain degree or a certain, which means it can be referred to some things that relates to the rotates, how the rotations. And when we talk about rotations, okay, we need to know, we need to define that in one rotation, we definitely will see, for example, when we have some Cartesian coordinate like this. So when we started at the very first um, 0 degree over here, so we can say that at the 90 degree or 90 degrees, uh, after the 0 degree, so we achieve 90 degrees, and after that, another 90 degrees after the 90 degrees, which is we reach to the 180 degrees, and 90 degrees after 180 degrees, so we reach to the 270 degrees, and another 90 degrees after the 270 degrees, we will reach 360 degrees. But right now, we are talking about angle, but in degree. Okay, angle in degree. So as you know, when you talk about angle, okay, it can also relates to the terms in radian. Okay, for example, we have here a 2 pi, okay, a 360 degree is equivalent to 2 pi radian. Okay, is equivalent to 2 pi radian. Okay, 160 degree is equivalent to pi radian, and of course a 90 degree will equivalent to half pi radian. This is not the pi that we are talking. It's like a number of 3.5142, but this is the value of 2 pi is in radian. As you can see from your calculator, you have a degree mode and you have a radian mode. So this 2 pi radian is in radian mode. Okay, so 300, so you can use this uh, what we call that as the number of degree. For example, 360, 180 degree, and also 190 degrees. We can change it in terms of what is the value in terms of radian. So we have 2 pi for 360 degree and a pi for 180 degree. Okay, so that is a little bit conversion between a degree to a pi radian. So we need to know that a pi radian, for instance, we have what is 1 radian? Okay, 1 radian is equivalent to 360 degree divided by a 2 pi. So if you want to know what is a 1 radian, so 1 radian is equivalent to 360 degrees. Okay, it's very easy. You bring this 2 pi radian to the bottom part, okay, to the denominator part. Okay, so 360 degree, you divide with the 2 pi in order to find what is 1 radian. So in this case, 2 pi radian is equivalent to 360 degrees. Okay, just take one, just take one. Well, and then what happens to 1 radian? So 1 radian equals to 360 degree over 2 pi. Of course, now we want to know what is 1 degree. Okay, so 1 degree is equivalent to what? Okay, so it's equivalent to 2 pi radian divided by 360. So So it's a reciprocal of the 1 radian, which means 1 radian 260 degree divided by 2 pi, and at the same time 1 degree is equivalent to 2 pi over 360 degree. So because of that, we can find some little bit conversion from this part. Just take one. Okay, if you really like 360, then just take 360. Normally, in my case, I always use 2 pi as a 360 degree, or maybe I can use a pi as a 180 degree. So it's up to you which one you want to take as the conversions. Okay. So first let's look at some fundamental ideas. You know that the distance s around circle is given by 2 pi r. As you know, when we are given a circle, the circumference of the circle is called the circumference or the outer length of the circle is what we call as 2 pi r, or we noted that as the circumference of the circle, where r is the radius of the circle. Dividing both sides by r results in the expression shown here. Okay, so now we have s equivalent to 2 pi r, and s, as you know, is the circumference. Okay, circumference, which means lilitan, circumference that equivalent to. Okay, and if we try to divide all both sides with r, so this one is divided by r, and this one is divided by r, you can cancel out on the right side, but now you left with the s over r equivalent to 2 pi. Why the needs to do that? Okay, because we want to make sure that what is the unit for a pi. So it just says that this is a dimensionless quantity. Since s and r have the same dimensions as length, okay, that means s over r is l over l. Okay, so as you know, okay, 180 degree is equivalent to 2 pi, is a pi radian. Okay, it's a unit of rad. RAD stands for radian. Okay, so 180 degree. Degree is a very a small superscript of this one. Okay, superscript of 0. That means the degree that equivalent to pi radian. Okay, for a circle of radius r, like this one, okay, 1 radian is the angle, okay, 1 radian is the angle subtended by an arc length equal to r, subtended by an equal to r. Okay, for instance, okay, we may see at a certain circle like this one, okay, where there is a center of the circle in the middle, that means at the origin. So we can see that the S or the circumference is the length of the outer area of the circle. Okay, outer area of the circle is called circumference. The length of the outer parts of the circle is called circumference. Okay, of course, okay, the length from the center to the circle is what we call as radius r. Okay, that means you can say that for a circle of radius r, 1 radian is the angle subtended by an arc length equal to r. So this one. So we can say that when we have a radius of r, so we may see that there is the theta, and r can give you circumference. Take a look at the circle. The angle theta subtended by an arc length s along a circle of radius r measured in radians counterclockwise from the positive x-axis. Why is counterclockwise here? Because it started from the positive x-axis. Well, we can um, include the x and y axis in this very Cartesian coordinates. Okay, so the rotation started from the positive axis going into a y-axis. So that means we can look at the situation where the what we call that as, where this is one. Okay, um, the circumference, or what we call that as the r, the radius, okay, started from the positive x-axis is equivalent to positive, or it is counterclockwise. Okay, it's a counterclockwise going to the y-axis. Right. So, right, the angle theta here is an angular displacement. We call that as an angular displacement from the positive x-axis. Okay, look at the radius. Okay, the arc length, which is r, the arc length as that is equivalent to r when and you have a theta, that means that some angle, okay, that contains between the the arc that we have drawn, okay, from the positive x-axis. So we are saying that the angle theta is an angular displacement. So this is the angular displacement from positive x-axis, and s is the corresponding displacement along the circular arc. Okay, so let's take a break for 1 minute, 2 minutes because of Azan, right? Okay, so let's continue. So so again, theta is the angular displacement. Okay, theta there is the angular displacement, which means when theta multiply with r, so we can get s. Okay, so r, s is equivalent to r theta. That means s is the circumference or the arc length. That means panjang lengkuk, arc length, and it comes from the radius and also angular displacement. Okay, as we can mention during our school days in at maths, when we have s equivalent to r theta. So when we want to find the arc length, the panjang lekuk, so we use a radius, jejari, a radius, and also the theta. Now remember, the theta must be in radian. Okay, the theta should be in radian. Okay, so what is theta in here? We are correspond to that is because theta, okay, in this case we call that as the angular displacement. That means it's actually a displacement, but in terms of rotation. Okay, angular in rotation. Right. And the angle shown in the figure, okay, for instance, we have a figure here, illustrates the size of one radian, which is approximately 57 degree. Okay, one radian. As I mentioned to you, okay, uh, over here, where one radian is equivalent to 360 degree divided by 2 pi. Okay, so that is equivalent to one radian, and then you need to convert it to degree. Okay, the figure shows a top view of a rotating disc, okay? A rotating disc, and this is an example of a rigid body. So can you imagine this as a top view of a compact disc. Okay, normally, okay, during now we are hardly to find this, but if you can manage to see or to experience, to look into what is compact disc, it's actually a disc, a disc, CD, kita panggil CD, a compact disc. That's why I call it CD. Okay, so when you look into the top view, it's like this. Okay, when we may see, okay, the examples of a rigid body where each part of the body is fixed in a position relative to all other parts of the body. Okay, we can think of that the compact disc is like a very rigid body. That means it's not scattered, huh? And of course it's not scattered, and all parts has been confined into a certain area. Okay, so we fix all position relative to all parts of the body. When a rigid body rotates through an angle, remember, okay, when we talk about the motion in rotation, so everything when it rotates and give you some angle, all parts of the body also will rotate through the same angle at the same time. Remember, okay, so look at the figure. Okay, basically when we go, into the slide just state look at the figure on the left, but it should be look at the figure A. Okay, figure especially for the compact disc. That means here this figure, the axis of rotation is at the center of the disc, which is here, axis of rotation. Okay, a point P on the disc is at a distance r from the origin and move about O in a circle of radius r. Okay, now we set up a fixed reference line and assume that a time t equals to 0. So these are the reference line where it's all started. Okay, of course, when you look at the top figure, top view of the compact disc, we cannot see anything. Okay, it's just maybe a slightly with a figure mirror, or okay, maybe some disc will it's like a mirror. Okay, maybe we can put a figure, okay, on the top view of the disc. Okay, so this is like an imaginary line of the reference line. Okay, we just took one line so as a starting point. Okay, so when it rotates, okay, basically rotates regardless of maybe counterclockwise or clockwise. So in this case, it rotates clockwise, and from a reference line, now let's draw a point, one point as point P. Okay, a point P on the disc as a distance r. Now travel. Okay, let's see the point P now travel to a certain point, okay, to a certain value. Of course, it should travel straight line, but when when a body, that means body contains in that move in rotation, the body that move in rotation, normally it cannot move like a conventional way of motion. That means when you want to go straight, you go straight, but this one, okay, the when the body that means one point travels, okay, it did not travel in a straight line. Okay, that point is actually will be influenced by that angular displacement. Okay, this point P, okay, have now traveled to a certain arc length, as we mentioned earlier, to a certain s. That means after a time interval delta t, that means this is delta t equals to 0, and at a certain delta t, which means here delta t, that means there's a number of time, so the point P has advanced to a new position as shown in this time interval, the line OP. So that means the line between AO, the center of rotation, and P, where is our point, has moved through the angle theta. Okay, has moved to the angle theta with respect to the reference line. Okay, so the angle theta is measured in radian. Okay, so as I want to emphasize on the theta, it's not an ordinary theta. Okay, we did not use theta in degree. Okay, remember when you want to find the as the angular displacement theta, okay, it's not a degree. It's not in the mode degree, but it should be in radian mode. That means you need to convert your calculator to the radian mode, or you can do a simple conversion. Okay, so the angle theta is measured in radians and is called angular position. So it is analogous to the linear position variable x. Okay, notice also that point P has moved an arc length as measured along the circumference of the circle. Okay, the circumference, that means the arc length of the circle. And as you know, the circumference of the circle is given by 2 pi radian. 2 pi radian, which means equivalent to a 360 degree. Or in radian, we call that as 2 pi radian. Okay, that is the circumference. Okay, in this figure, as a point on rotating this move from point A to point B. So right now we get a little bit serious when we comparing those things. Okay, just now, okay, we compare our position from point P, so for point P on the reference line, and after sometimes when the disc rotates, okay, the point P have now moved to a new position, and because the point P moved to a new position, it created some theta. It created some angular displacement. So that's why we are calling that is the angular position. So in this figure, as the point on rotating this move from point A to B, for instance, we have point A to just like we did in point B in the previous slide. It starts at angle theta. Okay, it starts at angle theta and ends at angle theta final. Okay, theta initial and theta final. For instance, point B started at angle initial, and point A started at initial position, which is angle theta, initial angle, and then point B. Okay, when we move from point A to point B, now we will look into what is here, which means theta F. So the final position. So we are saying that theta initial is where the point is starting the movement, the motion, and the theta A ends at point A ends at point B. So at point B, we calculate back the theta F, which means the position or the angular position of final position. Then you can see it travels at the some distance. Okay, so when you look into angular, so how to calculate the angle? So it's just the same as we doing the delta x. Remember, the delta x is when you took uh, x final minus x initial. So but this one is in linear. Okay, how can we do it in angular? It's also the same. Okay, it's also the same. Why? Because, for instance, point A starting at theta initial here. This is theta initial. And point B will have a slightly bigger theta, which is theta final. So how to get the delta theta is between theta final minus theta initial. Okay, the same thing when you apply to the angular displacement. So the difference of theta final minus theta initial is called angular displacement. So that's why we are saying that delta theta is equivalent to angular displacement. And object angular displacement is the difference in its final and initial angles. Final and initial angles. We don't say position anymore because the position is related to the angle, because now the movement will be because of the rotation. Okay, so you cannot easily say that. Okay, it is the same as a linear motion. Of course, it can relate to the linear motion, but not the same as the linear motion. Okay, so the SI unit for delta theta is radian. So when you look into the value, we look to the question that they give you some radian, that is the angle or the angular displacement. For example, when you have a theta initial at 4 radian and the theta final at 7 radian, so you can see that the delta theta, the angular displacement is the T 3 radian. When 7 radian minus 4 radian, you will get 3 radian. Okay, so we use angular variables to describe, okay, the rotating disk, because each point on the disk undergoes the same angular displacement in any given time interval. Okay, so when you look into the compact disk, which is the CD, okay, the CD is compact disk. Okay, when one thing moving, okay, when one point is moving, let's say point, okay, a compact disk. So I don't have a CD over here. Say a compact disk. When one point move, okay, every point on the CD is also moving. Okay, so we cannot relate this one, this problem or this situation similar to what we experience in maybe in a theme park. Okay, that's a big swing. Okay, when we have a lot of peoples, okay, go to swing in a theme park. Okay, because when somebody move at a certain angular speed or angular displacement, so not every rigid or every points on the swing will move. But when you use a compact disc or CD, okay, when it move, when one point move from a certain, so every points on the CD, of course, the CD is a rigid thing. Okay, it cannot have a the CD is a rigid thing. That means we cannot break into a certain portion of the CD. Okay, the CD comes as a CD, right? So that's why we call that as a rigid body. Okay, so let's look into some things that we do to the this angular displacement. So we can also rewrite our equation of theta, okay, where the delta S is a displacement along the circular arc subtended by the angular displacement. So now we are ready to define an angular velocity. Okay, so just now we look about we say about angular displacement. So this is the angular displacement. Now we want to make sure how can we relate our terms in angular velocity. So it says that the angular velocity will be based on the delta t, which means the angular displacement, divide a delta t, the delta theta over, sorry, the delta theta over delta t. What is delta theta? Delta theta is the theta final minus theta initial divided by times. Okay, of course, the delta is the angular displacement and the SI unit is radian, but time is seconds. Therefore, you will get radian per second. Okay, which means the angular velocity is the radian per second, that is equivalent to angular displacement divided by time. So angular displacement divided by, okay. So for very short time intervals, the average angular velocity approaches the instantaneous angular velocity just as in the linear case. Okay, so the average angular velocity approaches the instantaneous angular velocity just as the same thing happens in linear case. Okay, so the instantaneous angular velocity of a rotating rigid object is the limit of the average velocity as the time intervals theta t approaches zero. Okay, I would like to recall back that the average velocity in linear, we have v average equivalent to delta x over time. Okay, but we want to find the v, which means the instantaneous velocity is equivalent to a limit of delta t approaching zero of delta x over delta t. That means we want to get we cannot have a delta t approaching zero. We cannot have a delta t equivalent to zero, but we might think that the delta x over delta t will be based on the instantaneous. That means we want to find the instantaneous. That means at that particular time, what is the velocity? That is for linear. But as we mentioned here, the instantaneous angular velocity is also the same thing happens in the linear. So we can say that. So the average from the average velocity, okay, the delta theta over delta t, as mentioned again, delta theta is the angular displacement divided by time. So you may get a radian over seconds. And if you want to find the angular, instantaneous angular speed, so which means we use the omega as a limit of delta t approaching zero of the average, well, average angular speed. Okay, so the instantaneous angular speed or angular speed has no direction associated with it and carries no algebraic sign because of the word angular speeds. So we take a look at this point, okay? It's very important. We take omega to be positive when the theta is increasing, okay? So omega to be positive when theta is increasing. How can we get theta increase? So that means when theta is rotating, the motion of theta is a counterclockwise. Counterclockwise. So when you have a rotational motion, so when theta, that means it goes that way. Okay, it goes that way, which means the motion is counterclockwise. Okay, the value of omega should be positive. Why? Because you can see that the theta is increasing. And vice versa, when theta is decreasing, that means the clockwise motion, okay, that way. This is clockwise. This one is counterclockwise. Okay, then the omega will be negative. Angular velocity is constant. The instantaneous angular velocity is equal to the average angular velocity. Okay, the figures shows a bicycle turn upside down, okay, so that a repair technician can work on the rear wheel, okay, rear wheel, tayar belakang, The bicycle pedals turn so that the time t initial, at that time t initial, the wheel has angular velocity omega initial, okay, t initial, omega initial, okay, and then the wheel has the angular velocity. The figure on the left, this one, and at a later time, theta final, so angular velocity also final. So a changing angular velocity leads to the concepts of angular acceleration. Okay, so from angular velocity again, okay, if from angular displacement we manage to have omega, and then from omega, which means the angular velocity, we manage to get alpha. That's what we call as angular acceleration. So what is angular acceleration? A changing angular velocity leads to the concept of angular acceleration. And an object's average angular acceleration during the time interval delta t is the change in angular velocity divided by delta time. Okay, it's very easy. Okay, the same goes to when you apply to x, x, then delta x over t, we get v, and then delta v over t, we get a. So same things happen to the angular part, which means we have delta theta, and then after delta theta, we get to omega. And from omega, we get to alpha. So positive angular accelerations are in the counterclockwise direction. Okay, remember, positive alpha is the counterclockwise. Again, why? Because when you apply, you will get a positive omega. Positive omega comes from what? Comes from a change in delta theta. Okay, simple as that. Okay, so when you want to find whether the alpha is positive or negative, depending on the motion. When the motion is going to the counterclockwise, the value should be positive, and when the motion in clockwise, it should be negative. And how can we relate that? You just doing the look at the equation of average acceleration, average angular acceleration is given by delta omega over delta t. That means change in omega, change in angular velocity divided by time. And of course, the SI unit will be radian per second squared. Okay, of course, when you look back, when you have delta x, okay, goes to v, we have v, and goes to a. So this one is the meter. For instance, we have a m per s and m per s squared. So the same goes to delta theta. Okay, then we go to omega, and then after omega we have alpha. This one is the radian. Okay, radian per second, and lastly, radian per second square. So it's quite easy to understand how can we get some angular. But first we need to know, we really need to make sure that we do understand that uh, where is our judgment when we talk about angular. Okay, where is our concepts? The concepts that we get from angular is quite clear now. Okay, because you need to know that degree, that means the darjah, degree is darjah, okay, cannot be comparable to radian because there is some conversion between a degree to radian and radian to degree. And here, if you want to discuss about delta theta that is related to the circular arc, then you can have some delta theta from the angular, from the words angular displacement. Of course, the angular displacement positive will get come it will get from the counterclockwise mode. Okay, counterclockwise mode. That means the rotation should be in counterclockwise in order to get, because remember when we do a rotational motion, the motion is started from the reference line, which means our x-axis. Okay, so how do we really understand that? Okay, because the reference line is at the x-axis, where that is our starting point. And then when it goes up, okay, you draw a reference line like this one, for instance, okay. So this is our Cartesian coordinate. So this is our reference line. And if you want to make sure that the angle increase, why we need to make sure angle increase? Because we want to have a sum theta. Okay, the theta increase, that means it comes from it should go towards the positive, why it should go towards the 90th degree. Okay, because 90th degree is here. So we want to achieve that. We want to achieve from 90 to 180 and goes back to the original one. We cannot have this one, okay? We cannot have the blue color. We cannot go towards because when we go towards from 0 to uh, from 360 to 270, that means our theta have become negative. When theta become negative, so it can affect the omega, and also it can also affect the alpha. So let's use our definition to solve a problem. Okay, for instance, if the angular velocity goes from the 15 radian per second, okay, if you get blank, okay, in order to find which value is this, okay, look at the unit used. Okay, for instance, when radian per second, so remember this one is the omega. Okay, from 15 to 9. That means it slows down from 15 to 9 radian per second in 3 seconds. The average angular acceleration during the time interval is what we call as negative 2 radian per second squared. Okay, that means it become a negative angular acceleration. Okay, so that's why when you have, for instance, we want to find the acceleration. So delta omega final minus initial, final is 9 divided by initial 15. Sorry, 9 minus 15, 9 minus 15 goes from, that means final is 9 and 15 is initial, so it becomes negative. Okay, become negative. Negative 6 divided by 3, so you will get negative 2 radian per second squared. Don't forget about the negative because it shows the rotation. Where is this rotation? Either is going counterclockwise or clockwise. By looking at the value, we know this is a clockwise position. So the negative sign indicates that the angular acceleration is clockwise. So it's stated here. Although notice that the angular velocity is still positive but slowing down, and it is in the counter clockwise direction. Okay. So I think that will be the end of our class. Okay. But I want to for okay. We just I will stop here. Does anyone have any questions to ask? Ada soalan tak?
No, sir.
Okay, great. Anyone else? Ada orang lain lagi nak tanya?
No, sir.
Okay, tak ada. Okay, so I think we will continue our lecture tomorrow. Okay, so I think that's all for today. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Thank you.
Waalaikumsalam.